Alrighty, welcome everyone to Advent to Code, the recap of the days I didn't get to during Advent to Code was actually happening. Sorry it took me so long to get to here. Obviously, like I said, I went on vacation for the holidays, and while I was on vacation, I didn't really get to do a lot of the Advent to Code I was doing. While I was on vacation, didn't really get to do a lot of these. And then, of course, at the end of it, I got sick. I'll let you guys guess at what got me sick, but yeah, so it's not until now that I've finally been able to finish them all. All the questions are now done. And then in this video, I will walk through all my solutions for day 19 through 25, explain what I did, and hopefully give you some insights into how I solved the problems. And if you are still stuck, hopefully give you some help as well. So at any rate, yeah, so let's start with day 19. Yeah, day 19 was probably a good idea. I didn't try to do this one when it happened, or else I would have been very tired the next day. But this is probably what I struggled the most with in terms of I spend the most time working on it. The TLDR of this problem is that you have a bunch of beacons and scanners in a kind of an area. These scanners can all scan and return the beacons that they can see relative to themselves. So you're given this big list of all these scanners and what beacons they can see and their location relative to the scanner that sees them. So you have the problem of you have 100 scanner or 100 beacons out there, but a specific beacon might be seen by 3 scanners. So the question asks you to take all these beacons and figure out how many beacons are actually out there, and kind of remove all the duplicates that are seen by each scanner. The extra trick with this is that you don't know the orientation of the scanner when it's scanning the beacon. So the x coordinates of one scanner to a beacon might be the z coordinate or the negative z coordinate to another beacon for another scanner. So you will find the common name of the game with a lot of these solutions going forward with these is brute force. I brute force a lot of them. I don't know off the top of the head, but this one in particular, the solution that I end up going with is brute forcing. Basically, I just load in all the points. Let me pull up the input here while it's make it easier. So here's our list of all the scanners and what the beacons they see and their relative coordinates to that scanner for the beacon. And so yeah, I just take these, I load them all up into a list of lists, with the index being the scanner, and then at the index is the list of beacons that they see with their coordinates. And from there, it is just a big brute force. Let me try and go step by step. So the first thing I'm going to do is I have to build up this combinations list. This list is basically all of the different combinations that a scanner can be at in terms of its orientation. So that means basically, x or positive x, positive y, positive z, negative z, but at any of the 3 locations, while making sure we don't have, x, z, negative z, because that makes sense. You only have one x, one y, one z, but they can be positive or negative. So this builds up just a combination of all those different things where we have, an x, y, z, x, y, negative z, x, negative y, z, building up all those combinations there. So that's what this is here for. And this is the driving force behind figuring out the brute force of where the beacons are to mix them. But with that combination now set, we get into the main for loop here, which is the actual brute forcing. So what we do is we go through all of our points, not once, but twice. We have the main for loop, which is kind of, this is the point we are trying to match against, I guess you could say. And the inner for loop is the points we are trying to match against the one above. The reason why this one starts at 0 or 1 instead of 0 is we don't care about going from the 0 scanner to any others. We don't need to build a mapping between that. We only want to build a mapping to 0. So that's why it starts at 1, not 0. We don't want to check the same one to itself. And then we get into the heart of the brute forcing. Basically, we take that combinations list that we had before, and what we do is we translate all of the beacon points for the scanner. We translate them by that transformation combo. So if this is, y, negative z, x, this will take all those points and translate them to their correct, I guess, logic here, which is what this does. Basically, I just store the x coordinate, the y coordinate, the z coordinates in what they are. So an x is a 1, a y is a 2, a z is a 3. If it's negative, that means flip it. If it's positive, whatnot. So this just kind of takes what it's given for the translation and actually takes the XY coordinates and correctly translate them to what you're telling it to do. And so then once we've now translated all those points to whatever given combination of translation we want, we now have to go through all those translated coordinates and try and manually map them to where we want to go. And this is where we have a second set of double for loops. The first for loop here is just going over all of the points that we now translated. So each one of the beacons in that the scanner we have goes through all of those, and then it goes through all of the beacons in the scanner we're trying to match to, basically one by one, and saying, okay, this beacon is equal to this beacon, and maps them up and offsets them and maps them there. Then it goes through and offsets all of the rest of the beacons by that amount we had to offset them, and checks if they are at a corresponding location of a beacon from the previous scanner. And that's where we get our matches from. If we have, if we take all our 3D world of beacons and we map up 2 beacons to each other, we then see how many other beacons match with that offset. If we get 12, great, we have found ones that match. We have found the scanner, 2 scanners that match, and as well as the orientation and offsets, and we store that. If not, we just keep trying, and that's again, that's where the brute force comes into. So the kind of overall logic I used was basically we have 2 scanners, we have a 3D world of scanners with their beacons, and I just go one by one, take a scanner or take a beacon from one scanner, map it to the beacon of another scanner, and then check the rest of the beacons if there are matches. If not, then we just go through and keep mapping different ones together and trying to find where they match. And that's my brute force. That's really what it comes down to. And then at the very end, I just build up. I had to build up a tree to kind of get from one scanner to a next, because of course, I might have scanner 1 maps to scanner 4, but then scanner 4 maps to scanner 0. So I had to build up a tree to know how to go from one scanner to 0, and the logic I need to take to get there. So that's what this does. And the very end, for both part 1 and part 2 are kind of the same. They're kind of the same in the fact that I just have to take a scanner, map them all to 0, and then in that case now all of the beacons are mapped, add them to a list, remove all the duplicates, and then it goes part 1. Part 2 is just then taking the scanners, mapping all the scanners' locations to be relative to scanner 0, and then finding the 2 that are furthest apart. Nothing too complex there. The complex bit is just getting this efficient enough and getting all of the offsets and all of the translations and transformations correct. That was the hard parts. I had the idea of what I want to do for right away, essentially, was kind of brute forcing this, but it did take a good amount of time to try and figure out the logic to get all the transformations and offsets and all that working. So this one was a doozy, but in the end I was able to actually get this one working, so I was very happy. But there's day 19. Let's move on to a little bit easier one in day 20. So day 20, yeah, I had to read this one because I kind of forgot about this one. This is one of the ones I did pretty quickly. I don't know if it's because I understood it quicker. I didn't feel like it was all that hard. The only challenging bit is that this is an infinite grid, but I'll get into why that's not a huge challenge here in a second. But anyways, TLDR is that we have a mapping of the ocean floor, and you can enhance this mapping by applying a formula to a 3x3 section of the map, and based upon the value you get from that, you can then adjust the center one to that new value. It's kind of, it's a terrible explanation. That was a terrible explanation. Let me try this again. The TLDR for this problem is that you are given a mapping of the ocean floor as well as a key, which we'll get to in a second here. The mapping of the ocean floor is essentially an infinite mapping, to where if it's not in the initial given values, it is a dark pixel. So each pixel can either be dark or light, and you can enhance this image and kind of or zoom in a sense by applying a formula for a given position. For a given position, if you take the 8, I guess in this case, 8 surrounding pixels to it in all 8 directions with diagonal, you can then make a binary number from that, from zeros and ones, based upon the light or darkness of the corresponding pixels, I guess, around it. And then you can take that binary number and translate it into a decimal, or a base 10 decimal, and you can get the light or dark value from the key at that given index, and then assign that positioned to what you just got. So in this case, this middle bit is now a light value instead of dark. So that's what it is. The hard part comes down to that fact that you can't just stick this into a two-dimensional array because, well, it's infinite, where they all start dark. However, that's not a huge deal in the fact that we know, based upon the number of steps, how big this will get. The reason why we know that is because every time we take a step, it'll expand by 1 in the x and y direction. The reason why this is because this each point only grabs the one surrounding it. So therefore, if you only grab the one surrounding it, you have to have a location in one of the rounds surrounding that's already been kind of mapped previously, or has already been kind of checked at. All of the rest of the infinite grid follow the same pattern. They're all going to be either all on or all off. In the case of the example, all off go to all on go to all off. So they just kind of flip back and forth. So it's easy to keep track of ones we haven't visited to or aren't affected by our current grid. So that's where the infinite isn't too bad. And then now, knowing that the grid expands by 1 in both the x and y direction, both positive and negative, we can kind of just, I'll go to my code here, we can kind of just build up our map in this sense, to where instead, I do a map here of our two-dimensional point, whether it's on or off, but I can control my for loop that goes through all of the points and does the remapping. I can control this to only increment or increase in size every step. So every step, our area we check grows by 2 in the case of 1 positive, 1 negative for both directions. And then from that, we just do the logic of read all 9 locations, convert it to the binary number, figure out what that binary number then corresponds to, and then change the point in the map to its value of a new light or dark value. So honestly, it wasn't too bad in the end. And then for part 1, we can just easily, calculate up how many are light, and then for part 2 is just increase the number of steps, and that's it. So hard part there is just being able to better understand the growth of the actual active viewed area and how to handle the infinite space. So anyway, that's day 20. Hopefully that makes some sense in helping you guys, but let's move on to day 21. All right, for day 21, we get into this sort of deterministic dice game, it calls itself, to where we have 2 players, they roll the dice, they add up the total of the dice, move their character around. I'll let you read the rules of this. It's not too hard. It's just, I don't want to try and explain this one. There's kind of a lot of moving parts to it. But the key bit of this is that it's a deterministic game, which means we can use our favorite method of brute forcing, because it's just a brute force. I'm sure there's because it's deterministic, I'm sure there's an easier kind of mathy solution for this. I didn't bother. I just went brute force style. So take a look at my code here. It just reads in the player 1, player 2 start position, and then we literally just go through and play the game. Part 1, because it's not, part 1 is just simply roll the dice values in that sense, and that they keep going. We are able to get away with just one big while loop, to where while the player scores less than 1,000, just do a roll, and just literally play the game, simulate the game. It's part 1's not too bad, actually. We just literally simulate it. Deterministic, again, only one path. It's not that bad. So that one's easy. Part 2 gets harder though, in the fact that it's still the same as part 1. However, it branches in the fact that our rolls now cause a branch in the fact that, the player can, God, where's the branch again? So I'm confused. I'm blanking now. Oh, when it rolls a 1, 2, and a 3 all at the same time. So that's where the branch occurs, because the player rolls all 3 numbers simultaneously in a parallel nature, I guess. So we have to deal with that, and we have to play the game, but the game becomes recursive on itself to then do the exact same logic we had above, but instead of it being a while loop, it's now we're in a recursive loop and just keeps playing. The key to this, though, is to build a cache. Cache is the only reason why this brute force works. Because of the cache here, we are able to significantly reduce the runtime. You see here, this part 1 ran in under a millisecond, part 2 ran in half a second. Without the cache, I don't want to know how long it's going to run for, but with the cache, basically as we get to a state of the game, once we have solved that state of the game, we can then add it back to the list, because anytime we revisit the state of the game, it will always give us the same answer. It always gives the same outcome. So by caching each game state, we are able to hold on to it and we revisit again, because this revisits game states very, very often. Instead of going down the whole recursive loop again, we can just skip that, pull out the ending state from their cache, and return that back up. And that makes this so much faster. So this one, brute force again, was the name of the game for day 21. Part 1 is pretty easy, you just play the game. And part 2 is the same thing, you play the game, but instead of having this overall arching while loop, the loop is the recursion, and that recursion happens, in this case, I guess 4 times? Yeah, or 3 times, but for each dice. So it's like, what, 27 branches per round. Yeah, so anyways, that is how I solved day 21. Let's move on to day 22 now. Day 22, I'll actually just pull up the advent code. Day 22 is called Reactor Reboots, and the TLDR of this one is that we have a list of instructions that either turn on or off a area of pixels, I'll call it. I don't know, an area of grid spots, an area of points, I guess, in the 3D world. So each line gives you the min and max for the y, or x, y, and z, and that gives you a cube, and into that cube it turns either on or off all of those points based upon the instruction it tells you. And from that, after all those instructions have run, you need to be able to calculate how many points have turned on or off. Again, the name of the game of this is brute forcing. However, well, brute force, I guess that's not really right. This isn't, it's brute forcing, I guess, but it's not really. It's okay, ignore that. It's not quite brute forcing, but the name of the game of this one is to go through all the cubes, but to break the cubes down once they overlap. That is the biggest key. So when you turn on a cube for the first time, obviously there's nothing in overlaps there. You're actually going to turn all of those points on. But if you turn off only a subsection of those because a cube overlaps, well, now you have an issue of you have these mixed points that are both turned on but then turned off, so you got to be able to calculate that. The name of the game with this is be able to take a cube and split it correctly into smaller cubes when you have ones that overlap. So the logic here is not too bad. Literally it's just building a cube, adding it to a overall list of cubes, and then at the very end we just calculate the volume of the cube. If we're turning the points on, we add that to the list. If we're turning them off, we don't do anything. We don't add it to the list. All we do is we just it's just used to break cubes down. It's not saved. So in the end, this cubes list is only the cubes that turn points on, and we can just calculate it by the volume of all those cubes, because that's how many points are on. But like I said, the name of the game of where this problem was a make or break for you is if you get this logic here. This logic is the logic that goes into breaking the cubes down into these smaller bits. Okay, quick edit I want to make. I was editing the video and I realized that my explanation for how the cube splitting logic worked was terrible. So I want to give another shot at this and explaining it to hopefully make it at least better than I had done it originally. So at any rate, for the splitting of the cube, basically you have to figure out where the overlap of the cube is and be able to take the on cube, I guess, or the area that it's on, that has been flipped on, and figure out where it's been overlapped and remove it. And one of the easiest ways to do it is to break it up into a maximum of 6 new cubes, with each new cube being on the or off the face of one of the overlaps. Obviously, if there is no face on the overlap, so say it's only a partial overlap, If there's no face to go off of that, then there's no cube that gets generated. The easiest way is to think about it if the overlap is in the middle. So say you have a big cube with a little cube in the middle that's kind of contained within the larger one, and you just want to remove that smaller internal one. You first going to start with the x's. So if you take from, for looking at it, take the face to the left, face to the right, and basically you can just split the bigger cube and just remove those entire sections, so that way the middle bit that's left has the cube in the middle that has the left and right faces exposed to the outside, but the rest of like the middle column is still all there. And then from that, now you have two, I guess they're not cubes, they're kind of just chunks. I guess cube's probably the wrong term. It's just a rectangular chunk, I guess. It's a three-dimensional box, I guess. Is box probably a better word. But at any rate, so then you have the two side boxes split off, and there are new cubes. They're all ready to go, be put into your list. Then after that, you can then go on to the y coordinates. So now the y faces, the face that are above and below, you again split it there at the face of the overlap. You now have the upper and lower boxes that can be removed and thrown off into the new cube. And all you're left with is just a cube in the middle with off the front and back faces are two more boxes. Again, split at the face, but break off the two boxes. You can move those two boxes now into the list. All you're left with is just the middle bit that has not been removed and is the overlap and is now kind of thrown out. So obviously that's like the case of where if you have just one in the middle, it's probably the easiest to understand. Obviously, say the cube's in the middle, but one face extends all the way out. Well, now you no longer have that right face or whatever face it is, no more face there to kind of get a box from. So it's just ignored with this logic here. So it's a bit hard to explain. It's a bit easier if you have like kind of something in front of you. You can kind of visualize, slicing off the side boxes off the face to remove it, and just keeping and slicing them off until you're left with just the overlay bits. But at any rate, hopefully that explanation does a little bit better than how I did it originally. I don't know. Again, this was done a while ago, so like my brain is sort of mushy on exact logic here. But just know that what comes down to this is break down your cube into smaller groups of the overlap. Either if it's turning on and on, that we don't turn on points twice, I guess, or if it's on and off, that way you turn off the ones that overlapped. Comes down to just checking the x and y's where the overlap occurs, splitting the cube that way, adding to the cubes list, and going from there. Yeah, I don't know what to say. So this just breaks down to, at most, 6 smaller cubes if the overlap occurs in that sense. So yeah, this is the one that's a little hard for me to explain, so sorry, but that's where you need to look at, is breaking the cubes down into smaller cubes. So at any rate, let's go on to day 23. Day 23. This is the one that I definitely brute forced and is definitely not fast or efficient. It solves its both parts in like a minute, over a minute, I think. It's running right now. I'll let you know when it finishes. You can see the timings. A lot of people solve this by hand, by just literally just doing the puzzle by hand. I thought about that, but I was like, I want to have code here to show you. I want to be able to show you this. So here's the code again. The name of this one was brute forcing. I completely brute forced this game theory, which is just solving all of the possible outcomes of the game and finding the one that has the least score to it. Well, I guess you could also call it mini-max. I think is also, it's not quite mini-max, but it's similar to that. I just call it game theory. Basically, we build up the rooms and hallways, we send it to this play method, and it just brute forces it. It goes to all of the rooms, moves all the rooms out if possible, recursively moves things out, puts them back in, calculates the energy used, always keeps track of the least amount of energy used, and then returns the score. The hardest part to this is just there's part 1, minute and a half. Part 1, I think part 2 is also a minute and a half, so about 3 minutes for both of these. Not very fast or efficient, but it gets it there quick enough, I guess, for me. I couldn't think of a better way to do it besides this brute force. So yeah, the only things to really watch out for are the logic of where the pieces can and can't move to, They can't jump over other pieces. They can't move to spots directly above the rooms, and just doing that. The one, I guess I will say, the one very important thing I did for this that made this way more efficient is that I only used one array for rooms and hallways, one array each. I don't copy anywhere. I originally had it to where hallway and rooms was copied for each of the lower recursive calls. That is not very fast. It takes a lot of effort to copy arrays. So in order to actually hit this lot lower runtime, instead of, it was like up in the like tens of minutes before this. In order to hit 192 seconds, I just use one array for both of them, and after the recursive bit calls, we just reset their state. So in this case, this piece gets moved to the hallway, so we reset the room position to 0, we set the hallway position to this piece. We then recursively call this based upon the new state, and after that's done, we then reset the arrays to the initial state before. So we reset the hallway back to 0, we set the room back to the piece, and this is infinitely faster than copying things through. So that is the one improvement I made that actually made this feasible. As you can see here, 92 and 83 seconds. Not fast, but I got it in the end. Again, brute force. It's how this one came to be. Nothing too fun about this. Just took a lot of effort to get there. So at any rate, day 24, the second to last day. Let's go on to that one now. Day 24. Yeah, here's another one that I had no idea, and I brute forced. This one, though, you can't brute force straight up. There's just not a way to do it. You have to get, I guess, sneaky in the way you brute force it. So this one, the code's not complex. Again, the code is really just brute forcing the logic for this. What I did for mine, though, is I translated the instructions to Java code. As you can see here, here's the translation. We just initialize all the 4 variables. And input, you just literally translate them all into Java code. You can see here it's running. It gives me Java code for the program that are the inputs. And from that, I pasted it into here and went about simplifying it or condensing it down. And that is how you solve this, is you just take the program and simplify it. This is the ending program that I got for our inputs. Basically, I got down to the point where there were only Z's and X's. All the W's were replaced by the actual input number, and Y was irrelevant at this point. Yeah, so we get down to just Z's and X's, and that's still not enough because, again, it's a 13 digit number. That's going to take Java way too long to go through all of the possible numbers in this. But we do get saved in the fact that the first 2 and last 2 numbers can be determined by just looking at the code. And if you look at the code, you'll see here, actually, well, to go to the end, you'll see here that in order for this to return a 1 in the X, I think it was it a 1 or was it a 0 in the X? Either way, there's a 0 in the X. So the only way for a 0 to be in the X, you get this statement where X minus 5 has to equal number 13. Well, that means X has to equal one of these numbers, right? Well, if you look at the logic and how it works, the only way for X to do that with Z being 0, you have to get back to the point where all of this logic where you have the Z has to kind of undo itself. And for the very last thing, Z has to be a number less than 26. Well, only placing a number less than 26 is this initial state of number 0 of the first digit plus 13. So you can, okay, the first digit plus 13 has to replace this, so you get digit 0 plus 13 minus 5 equals number 13, which just simplifies down to here, number 0 plus 8 equals number 13. Well, you only have one option there. The only ones that matter are if number 0 is 1 and number 13 is 9. So there's your digits here. Those have to be those numbers. Do the same thing for the second to last, because you can also do it because of the fact that this Z is always multiplied by 26 no matter what path you get down to. So the second to last number will always be number 1 plus 10, and then minus 3, which you get here to number 1 plus 7 is number 12. Which in this case, again, just like before, it leaves you only 2 options this time of either 2 and 9 or 1 and 8. In the case of part 1, the larger number that you'll get is if you have a 2 here, because 12 whatever is greater than 11 whatever. But in this case of part 2 we want the smallest. This must be smallest, I think. We want the smallest number, in which case 1 is smaller than 2. So we get to this, and then if you use this as your starting number, you can then brute force the rest of these by just brute forcing it, which is what this logic here does. This just goes through all the numbers, it ignores the first and last 2 numbers, and then just brute forces the remaining 8 numbers. I forget what it is. Yeah, that's how I get part 1 and part 2. As you can see here, it takes a second. It takes 7 seconds for part 1 and 72 seconds for part 2. Not fast, again, but brute force works. I'm getting them shows another more math stuff like I used for the first 2 numbers that you could use for the rest of them. I just don't want to use it because this works. I was done at this point. Day 24, I had enough of this one. This one took me a while to solve. I tried it a bunch of different ways, but at any rate, that's how I was able to solve day 24, more brute forcing. Again, that was a very common theme for me. But at any rate, let's move on to the very last day, day 25, and let's get to this one. Alright, day 25. Let's actually pull it up here on the sea cucumber one. Luckily, this one isn't actually too bad at all. There's some nice visualizations. If you go on to Reddit and stuff, you can see how how it looks. But the TLDR of this one is that you see cucumbers. Cucumbers can only move in one direction, and that's really it. In our case of our answer, we have 2 herds of them. A herd can only move in one direction, so we have 2 herds of them that have kind of collided. One herd's going down, one herd's going to the right. And you basically just iterate until cucumbers no longer move. There's some logic and when they can move and what happens when they get the edge, so they kind of flip back around to the start. I'm not gonna worry about that right now. But yeah, there's the logic here of how they can and can't move. Just using that, it's pretty easy. You just go through them all, and you just make them move. You just step through it, you calculate them, you move. This one's probably one that you don't really need help on. If you've gotten to this point, you can probably do this one. It's just going through each step, moving each herd one at a time by the logic, and going to the end. Yeah. Got this one inside 2 seconds, so at any rate, there is day 25. That is the end of Advent of Code 2021. Hopefully you guys enjoyed it just like me. I'm gonna go get some water because I need some water after it's dry. But anyways, thank you guys for being here. Thank you for being on this journey with me. Hope you guys enjoyed. I will see you guys all next time. Peace out.